Welcome back to Module 3 on the Grokking Artificial Intelligence of Things. So in the previous video, I talked about how artificial intelligence is different from trying to create a artificial human brain or to create something that thinks like a human. That was an original aim of artificial intelligence, but over the years, actually, people have realized that it's very difficult to achieve, and they've reduced their aim. So no, the current definition for AI is actually to mimic intelligent human behavior rather than to think like an intelligent human being. However, I would say that there is actually a related field called artificial general intelligence. So the word general here is important because it's not AI, but AGI, artificial general intelligence. And this is actually a new field that is actually dealing with strong AI. That means we are trying to create systems that can mimic the way humans think. Now, it's important because this is different from AI. And secondly, there are many problems that actually are still confronting us today. Things like climate change, where the human intelligence alone may have a part of the solution, but we are not able to solve it completely. So if we are able to create something that can think like us, perhaps this new form of intelligence, the artificial general intelligence system, is able to come up with solutions that we ourselves are not able to think of, right? So AI is definitely not something that we can rely on to solve problems like wicked problems like climate change, but artificial general intelligence is. But this is actually the field that has been the stuff of Hollywood nightmares. So I think many of you may remember this fella here and also Skynet from the Terminator set of movies, where we have actually AI systems or robotic overlords taking over the world and trying to basically eliminate humans from the world because they feel that systems actually infer that humans are actually the cause of the problem, therefore they should be removed, right, from the world itself. So this is actually is oftentimes portrayed in the Hollywood movies. But how close are we to this kind of reality? Now, we actually have pretty sophisticated computer theory. So we have actually designed and understood well-known processes like how to play chess. So 30 years ago, we already have the best computer program, Deep Blue, beat Garry Kasparov, the world's best grandmaster chess player at the time. And more recently, we have a computer program, beat the best Go player or Weiqi player, a game that's a couple of thousands or millions of times more complex than chess. And we also have the theory for things like communication theory by Clark Shannon here. We have engineering know-how. But the path to create something like a rocket engine where we can combine strong engineering know-how with deep theory that can understand general intelligence, right? How we are able to process many, many different intelligent behaviors in our brain. We don't have the theory to do that, and certainly we don't have the engineering know-how to create something as complex as the human brain, which has trillions of interconnections in a 3D complex organization. So really, for artificial general intelligence to start being able to process things like a human, the way the human brain is able to process, the path is actually quite unknown at this point in time. So neither do we have the general theory, nor do we have the engineering know-how to actually achieve this. And the current approaches that we use for achieving very remarkable results in AI, such as deep learning, perhaps they are not the actual approach that we should be using to achieve this artificial general intelligence. Now, this opinion is not just by me, but some of the best brains in the world in the deep learning field. Geoffrey Hinton here, the father of deep learning, and Demi Hassibis, who is actually the CEO for DeepMind, the company that came up with the Go player, the best Go playing program that beat the world's best grandmaster at Go. Both of these gentlemen also think that we are actually nowhere near to reality in achieving artificial general intelligence, because The approaches that we're using for deep learning and even for deep reinforcement learning, the technique that was used to build DeepMind's AlphaGo that beat the world's best Go player, they perhaps are not the real approaches to be used for solving this particular puzzle of building an artificial general intelligence system. So bottom line is really, it is still very far away, just like nuclear fusion. It's just a couple of years away, but it's always just got a couple of years away because we don't have the underpinning theoretical knowledge to actually achieve it. But for practical use of AI applications, really, we don't really need AGI at this point in time. So we should really not be too worried about the robotic overlords taking over the world. Perhaps what we should just focus on is how we can leverage on the capability of understanding AI better and leverage on its current abilities to help us solve the various problems that we have today, instead of waiting for AGI or fearing AGI. So AI actually is not just one type of approach, but many different approaches. So the term AI actually is a broad umbrella of many different approaches to creating this intelligent behavior or mimicking this intelligent behavior you see in humans. So here are some of the, there's a blog source here. So this is actually from the book by Pedro Domingos, and there are actually 5 main approaches that are being used to to create artificial intelligence today. The one that's very popular at the moment is the one that is used to build deep learning. Neural networks is their favorite type of algorithm. And for this approach to artificial intelligence, they are trying to basically mimic the way the human brain works. So in the brain, there are many brain cells or neurons. So we have artificial versions of those or artificial neurons. And the way our brain actually learns is that the connections, right? The connections between the brain cells, the synapses, they change their weight or change their strength whenever we learn something. So by the time we actually end this course, your brain should have changed slightly by definition, because that's how you learn something. The structure of your brain changes slightly in terms of the interconnections. And we have trillions of these interconnections in our brain. So we try to make a similar arrangement in the neural networks, but this is an artificial arrangement. So we have artificial neurons, and the connections between the neurons are what we call weights. So we adjust the weights in order to make the artificial neuron learn something. So this is actually currently a very popular approach, and it's an approach that underlies deep learning. It has made very remarkable progress in the last 5 years. Things that were long thought to be unsolvable have been actually solved by this particular approach. But the others are not gone from the scene. They are actually having still many application areas that are able to use them very effectively. Neural networks is not a silver bullet to answer everything. There are actually problems that neural networks are actually not very good at. For example, if you do not have enough data to train a deep neural network, you shouldn't use this algorithm because the result is likely to be worse. Or you need explainability. Again, neural networks are like a black box. They are very poor for explaining how the decision is being made. So there are some problems where you need to not only get the result, but you also need to have a way to understand how those results were being derived. So something called explainability. Just to give you an example, let's think about insurance premium. You're trying to use the neural network to compute the insurance premium, and you find that actually you are paying, the algorithm determines that you are paying a higher premium than your friends, right? Through some sort of relationship that it actually discovers in your personal profile. But it's not able to explain to you as the client, right, why you should be paying a higher premium. It just tells you that based on what it can recognize from the patterns it sees in all its data, you as a person should pay a higher premium than your friends. But it cannot explain to you how that decision is made. I think this is not acceptable. So for this kind of problem, like medical diagnosis, as well as insurance premiums, you need to give people a reason or an explanation how that decision was made. You cannot just tell them this is the decision and you have to take it or leave it. That's just simply not acceptable, right? So for neural networks, actually, they are black box approach. Although they are very accurate in coming up with correct action to perform, they are very poor at explainability. They cannot explain to you how that particular decision is recognized from all the thousands and millions of patterns that are actually being presented to it in the training data. These other algorithms like decision trees, they work very well for in terms of explainability. So you can see that some algorithms they may not be as accurate as neural networks, but they have other characteristics that are better. So the symbolist approach or the logic-based approach is actually the original approaches being used by AI scientists to create AI systems. So they are still very much in use today, especially in the cases where you can actually get the an expert to explain to you what the rules are. So think about diagnostic systems like a medical diagnostics, or you're trying to decipher what's wrong with your aircraft engine. It's something that's designed by a human. You can actually ask the experts who design the system, what are the rules to use to diagnose what's wrong with the particular device, be it a disease, or it's a lift, or it's the aircraft engine. You can ask the people who are the medical experts or who are the engineers who design the system to give you the rules. Now, if the experts are not present or the experts are not able to express what the rules are, you are still not lost because you can still infer the rules from using algorithms that learn from the data, such as decision trees. But this one, the humans don't come up with the rules, but decision trees, a machine learning algorithm will learn the rules from the data itself. But it's still a rule-based approach, a logic-based approach. They are still very much in use today. Okay, so it's not, although it's an older technique, it doesn't mean that it's gone forever. Some other techniques that's based on probability, it may not give you an accurate result like decision trees or neural networks, but they are able to handle very large volumes of data because the algorithm is more efficient. So you have huge volumes of data, and you want to have some amount of explanation in terms of probability or likelihood of something happening, then this group of algorithms are good because they give you some explainability and they can process very large volumes of data. Same for this one, cost support vectors. They are based on how similar your data is to your present data set. So that's why it is called analogizers. These kinds of algorithms are very good in certain contexts like cybersecurity, where you do not have a mathematical formula or mathematical model to explain the phenomenon. All you have is the existing data. So the existing data that you have, you need to try to make an analogy. How similar is the pattern that you're trying to decipher related to the similar to that data? So maybe one of the things that you're trying to do is to detect a fraud, something that's very anomalous or very unusual, but all you have is the present data. So that present data forms the base to determine what is the common occurrence, right? The so-called normal data. So by comparing against the normal data that is represented by the circle here, we can determine all the red ones, right? The ones, the anomalous data, the ones that may be fraud or may be normal data, but at least we have some indication that they are a bit unusual and we should look at them, right? So the basis for this kind of algorithms is that they compare against the existing pattern that you see with your present data. No mathematical formula, not based on probability, not based on some thing like entropy, or not based on some sort of pattern that is being learned in terms of weights, but based on just comparing against the existing data that you have, analyzers. Okay. And lastly, we have one group of algorithms that have been very popular maybe 20 years ago or so. This is actually what we call genetic programming. Right, and the purpose of this is really to try many different approaches to solve the problem, just like what we have in evolution, right? So this is also called the evolutionary approach, right? So the idea here is to permutate many combinations and see which is the one that will survive, right? The one that survival of the fittest, right? The one that actually gives you the closest answer out of all the possible combinations or permutations you generate. Now, this actually has not been so actively developed, but currently there are actually a lot of active research to try to combine this approach, the evolutionary strategies, with neural networks so that we can solve problems in neural networks in a more scalable, more parallel manner. So this is actually one of the big advantages of genetic algorithms. They are more suitable if you have a parallel computing architecture. Okay, it's more easily to parallelize compared to a neural network. So by trying to solve a neural network using evolutionary approach, actually you can run it on a cluster of computers and you can get the answer faster. So bottom line that I wanted to just reiterate again is that all these 5 approaches, they are still very much actively in use. And in fact, there are now hybrids of different combinations of these different approaches to try to get the best result with these algorithms. So I'm going to just show you one activity now and also explain to you why this particular example is important to understand as we see what is the advantage of trying to learn from the data useful, what's something called machine learning, why is it useful as a way to approach artificial intelligence as opposed to the logic-based approach, right? So in the logic-based approach, you often need to have lots of data or you need to have expert inputs. Well, what happens if you don't have the experts around? All the experts cannot explain to you how to do something. So this is actually, you can actually click, just pause it and just go to this site. And I'm just going to show you from my browser as well. Okay, welcome back. So this particular example, I put it on my Chrome browser. So in this particular example, the problem that this bunch of programmers were presented with, and this a couple of Japanese programmers, they were asked to create a program that can draw Japanese cartoon figures. Now they are programmers, they are not artists. So they don't know how to draw Japanese cartoon figures, even though they are in Japan. So they were saying that, hey, why don't we ask some experts, artists, manga artists, how to actually draw a picture like that? But they quickly realized that actually the manga artists do not actually have a step-by-step approach or a step-by-step way to draw a manga picture, because it's not something that you learn by doing it in a algorithmic approach, right? Something that you do, so first you draw this, then you draw that, then you draw something else. It's not something that they actually do in a step-by-step. In fact, what they have learned, they actually do by experience, right? Not a step-by-step approach. So how do you actually do this step-by-step? It's not really possible for even if you have an expert there, they cannot explain it to you. However, they quickly realize that, hey, what we have is that we have thousands and thousands of examples of these manga pictures or cartoon pictures present in Japan. So if we can design a program that can learn from these pictures or learn how to draw from the pictures themselves, then we will have solved the problem. And this is precisely what they did. So actually what they did was they used a machine learning algorithm to build a program that can learn how to build a program that learns how to draw manga pictures. Now the program that is learned or built automatically from the data is what we call a model. So in this example here, the models, the list of models here, they are not fashion models, but they are actually generated programs, right? These mathematical models or AI models or machine learning models, they are actually programs that have been automatically generated from the data by learning from the data. So you apply a machine learning algorithm to the data, and the output of that learning process or training process is actually what we call a model. So the model really represents a program that has learned how to draw the pictures after it's been trained with thousands and thousands of manga pictures. Now the training process takes a long time and it's been run in the cloud, but after it has been trained, all we need to do is download the model and it can run very fast. In fact, it can run on in our own browser. So if you click on generate, it will always generate a unique figure for you. Right, so I can pick, as I want a blonde hair, generate something for me. In fact, I can actually click on generate again. Or if I want black, I can also generate different figures for me. Now, what it is doing currently when I click generate is that it's using the techniques for drawing that it has learned from the data. It's not actually combining different combinations of blue eyes or black hair together, because if you combine several different features together into one new picture, it will look very scary, right? It won't look even like any pleasant figure at all. It's what it has actually learned from the data is actually different drawing styles. And by changing the parameters, it just adjusts its drawing style according to what you have selected. And to show you that this is actually the case, you can click on transitions. You can set the starting image, maybe this girl. And I can do another tab here, and then I set the ending image. I want this one as the ending image, and you can see that the program is able to generate slow changes in the drawing styles from one image. So you can set any starting image to any ending image, and it can actually adjust the drawing style from one image to the other. So this is just to show you that really it's not actually just randomly combining different facial features together. It's really learning how to draw the picture from the examples that were presented to it. So this is actually a case of a generative model that can really be used for applications. You can use this picture that you generate as your own avatar. You can also use it to just decorate your own website if you want to, and you can just play and go crazy with this. So I will leave it to you to play around with this particular application. Each picture that is being generated actually unique. Is going to be different, and depending on the model, because each of this is trained with different data sets with different parameters, they are able to generate slightly different looking pictures, right? Even though you press the same parameters, you can see that it will generate different pictures. Okay, welcome back again. So from the activity, you can see that really the advantage of machine learning, which is a way of learning how to do something from the data itself. Now, the advantage is this: even if you're experts, they may not be able to decompose the problem for you. And for some new problems like COVID, uh, the experts don't exist because it's a new disease. Nobody really understands the pattern or the characteristics of this. How do you relate the symptoms to the actual disease itself? So for this kind of problems, really to be able to learn the pattern from the data itself is a tremendous advantage because you can't solve this kind of problems by trying to break it down to a step-by-step approach. It's just not doable. Think about something like self-driving cars. It also cannot be done by just trying to break down the process of driving a car into a step-by-step approach because that is not how humans drive a car, and that's certainly not going to be the way how an AI will drive the car as well. It just needs to learn the correct approach from the data instead of trying to break it down into a rule-based or step-by-step approach. Okay, let's continue with the next part, which is how is AI different from machine learning. So AI is actually a broad area, so there are many different approaches to AI, including getting the rules from experts and just coding into a rule base and just just fire the different rules to see which one of them will actually apply for that particular context. So there's a rule-based approach. It doesn't require you to learn from the data. So a logic-based approach, you do not need to use machine learning. So machine learning is a particular subfield of AI, right? So AI is the bigger area. Within AI, you have one smaller area called machine learning, where the focus is to try to learn from the data. So machine learning is actually a subfield of artificial intelligence that's concerned with implementing software that can learn automatically or autonomously from the data itself. Okay, you don't need a human expert to teach it how to learn. It's an algorithm that can learn the pattern. All you need to be worried about is actually to present it the suitable set of data so that the algorithm can learn from it. And as I mentioned just now in the Make Girl movies example, the model is actually the output from this process. So when you apply machine learning algorithm to a set of data, the output, the program that's built from the data, by learning from it, is called a model. Let's try to understand that definition from a layman point of view. So if you're trying to solve this particular program by a human playing it, and the goal of this game is really to toss the ball into the waste paper basket, but you have a fan, annoying fan aside here that will keep blowing the ball away. So you as a human will try to learn the game by trying different angles and flicking at different speeds. Now that's human playing the game. Now, if I try to program the solution using a traditional approach, so-called algorithm approach, I would need to have some formulas, okay, for how fast the fan is blowing, what's the angle, and if I can add in all these formulas, I can actually program it such that I will flick the ball at exactly the right angle, and it will be blown by the fan. It will just drop right in the center with no problem at all, and it will work every time. However, the problem is this: the moment I change the fan speed, or if I move the fan to another place, the original program that I have is very brittle, right? The moment I change any conditions, it won't work at all. So this is actually a problem that we will find in many programs or software that we generate today. They only work with a particular set of circumstance or environment. The moment we change something, is the program's not able to automatically adapt to the new the changes, and we need to actually reprogram it or write a new program to replace the old one. Now, if we try to solve this problem using a machine learning way, we will actually try to learn from errors or trial and error, just like humans. So initially, the program will just throw the ball all over the place and out of the not the correct set of values, but eventually it will chance upon a correct value that will actually drop the ball straight in. And as it drops the ball into the basket, it's going to be able to learn from the correct examples versus the ones that falling all over the place, that it should repeat the same examples over and over again to get into the ball, right? So you just need to give it many opportunities or data to learn from, and eventually it's going to be able to learn to play that game. Now, such an approach is also more flexible or adaptable. So even if you were to change the fan speed or change the fan position, of course, given the initial examples, the ball will start flying out of the waste paper basket. But if you keep trying different approaches, eventually you will learn that, hey, given the current circumstance, actually I need to adjust my approach maybe to actually change the angle or change the speed. Same program, it will just be able to learn from the new data without having you to rewrite the whole entire program. So this is actually the advantage of a machine learning approach. It is able to solve problems where the answer is not very obvious because there's no human expert to tell you what the rules are. And secondly, it's able to basically adapt to learn what the rules are from the data itself. So we can see that, in other words, another definition for machine learning, a more technical definition, is actually a computer program that's able to learn from experience with respect to some class, a task, and improve its performance. And its performance in that particular task will improve the more experience it gets. In other words, basically, machine learning for a task is it means that in machine learning for any task, a machine actually improves its performance the more experience or the more data it has. What are some of the pros and cons for this? So as we can see, it learns autonomously from the data. So you do not need a human to be there teaching it what to do. Just need to present it with data. The more data, the better. Secondly, is that you do not need a human expert to decipher what the rules are. So you do not need somebody with experience to understand the business problem to sort of define what the rules are. So for some problems, really there won't be any human expert because novel problems like coronavirus, the rules are not known, right? You can only determine the pattern from the symptom database itself. Learning from the database or learning autonomously from the data is the only way you can solve such kind of problems. And the third pro is that really, if you have enough data and you have sufficient computational resource and the problem is specific enough, eventually the system will reach a performance that's better than the humans that help it gather the data. It's just like what AlphaGo has proven. Even though the world's best Weiqi player was long thought to be unbeatable by beatable by machines, eventually the program that was trained by DeepMind by playing against human players, playing against better and better players, eventually actually it has learned enough about the game to really beat the world's best Weiqi player or Go player in 2016. And it proved that point that actually machine learning approach can actually achieve superhuman performance even in the most complex game that's been known to man. And the good news is that actually after it has beaten a human, actually the program AlphaGo was actually retired from the Go competition, professional competition, so that humans can still enjoy the game without having to compete with machines. Because the point has already been proven, and there's no point in just leaving the machine in the competition circuit and spoil the game for humans. So we humans are safe, right? So the other thing is that actually AlphaGo has improvements after that competition with the world's best player, and the way they actually improve is play against itself, right? Because it's already beaten the best human player, so you can't play with any other human player. So the only way to actually improve the performance of AlphaGo Subsequent to the competition, was ready to play against itself. So it just play against itself to improve its performance. Okay, what are the cons? We need to have data. If you don't have data, then there's no need to talk about machine learning, because machine learning learns the patterns from the data itself. So without having the data present, you might as well go back to heuristics. That means rules of thumb that you gather on how to solve the problem. They would be more forthcoming in terms of a solution than trying to learn from data. Because what you learn from the data is likely to be nonsense because you don't have enough data to learn from. Secondly, the second con is that sometimes for some algorithms, what is actually learned is perhaps too complex to really explain or easily decipher how that decision being made by the algorithm is actually being made. Now, this is good enough that you can just have an accurate output without understanding how that relationship is actually learned within the data itself by the neural network, but it's not for all problems. So just now I explained to you that for some problems like insurance or even medical diagnosis, you really need not just the output, but also an explanation on how that decision was made, because it's not acceptable that there's no explanation or relationship. How is it actually, how the different factors actually relate to each other. You cannot just tell the user, hey, you need to pay this amount of money, but we cannot explain to you why you need to pay this amount of money. Not acceptable for those kind of applications. So there are application areas where machine learning algorithms are constrained, and we have to use some algorithms that have better explainability properties as opposed to the best algorithm. Okay, last con is that really machine learning is very innocent. You will just learn from the data, whether or not the data is good or bad, right? So you can actually present adversarial examples. You can purposely try to fool the machine with bad examples. So one of the stories that I often tell about this was that several years ago, Microsoft actually came up with a very revolutionary new chatbot technology that can learn from its interactions with users, Microsoft Tay. So it went well initially. Microsoft Tay was introduced to the internet and it started learning from the users to be smarter and smarter. But after a few short period of time, of a few days actually, they needed to kill Microsoft Tay or remove it from the internet or stop it. It learned from the data, it learned from the users, but this being internet is a chatbot on the internet. It started learning all the bad things from internet users as well, not just the good things, right? It started learning to be racist, learning to be bad language, and learn to be paranoid, etc. All the bad things it started learning from the internet users, because internet users were just presenting it data, but it was all bad data that it was learning from. Right, so this is the other thing that you should be careful of. Machine learning is very innocent, like a child. It'll just learn from the data, whether it good examples or bad examples. So you have to be careful with the data you presented. Now, if the data is biased, it will also learn the bias relationship. It will just replicate the human bias that may be present in the data because it doesn't know the difference. It's just learning the patterns it sees there. It is amoral to some extent. Right, so we come to the end of this first part about the AI as well as machine learning. So I hope to see you again in the next video. Thank you for your attention.